Um, let's see. So this is joint work with Nina Balkan and Yishai Mansour. So the starting point of this work is, I think, quite related to the motivation of Asu's talk, which is that games are really an abstraction. And so when you take some real-world setting and you model it as a game, what you try to do is you try to identify the most important decisions of the participants and the main factors in their payoffs. But there's always going to be low-ordered factors or variables that you weren't able to model. So for instance, if you want to model people choosing routes on the way they drive to work, you might model this as a congestion game. And it's true that maybe the main factor in determining how long it takes me to get from home to work is the route I choose and the route of everybody else. But there's all these other issues. There's the timing of the traffic lights, whether there's construction, and all these other things that go on that are not part of the model. In addition, it may be that there's some players whose incentives are not really modeled well at all. There's a few people who are not actually trying to minimize their time. Some of them are talking on their cell phones or whatever. Okay? And so the high-level question is, how much impact can these sort of issues have on natural dynamics of the system? Okay? And so, for instance, in particular, we'd like to think that if we're able to get people into a good equilibrium, and the players are selfish and reasonably myopic, then behavior will stay there. Right? And we could so safely walk away and be confident that the system is going to stay in a good state. Right? But what if there are these small fluctuations in the underlying cost or payoff structure? Could this cause natural dynamics to spin out of control and then something crazy to happen to the system? All right? So I'll get to the formal model in a few minutes, but the high level is going to be that we'll imagine that between time steps there are small fluctuations. Maybe one day it's raining and the next day it's not, and these cause small fluctuations to the cost structure. And players do best response dynamics in between these events, and then we'll want to see what happens to the social welfare, social cost of the game. Okay? And another setting we'll think about is where there aren't fluctuations in cost, but instead maybe a few players who act unpredictably. Okay? And then the question is, okay, in that case, what happens? Can these small fluctuations or a few unpredictable players cause natural dynamics to get the system into a high-cost state? Okay. Now, high level, there's a few different ways this kind of thing could happen in a game. It could be that your game has the property that small changes cause all the good equilibria to disappear. And all that's left are bad equilibria, so what's going to happen? Things will maybe go off to this bad equilibria. What can you do? Okay? Also could be, depending on your game, that your game has the property that bad behavior by a few players could cause bad things for everybody. Like, I don't know, the nuclear warfare game, for instance. Okay? All right. So, but actually, we're going to be focusing on games where neither of these happens. Okay? And instead, we're going to be interested in games where neither of these happens, but instead, though, you could still have issues through a kind of more subtle interaction of these fluctuations with the dynamics, where somehow these fluctuations cause your dynamics to sort of head in the wrong direction. Okay? And our focus is going to be on this last issue. So in particular, we're going to be interested in games with the following properties. So first of all, we're going to focus on potential games, actually exact potential games. And we'll be looking at best response or better response dynamics, so players moving to the best response to their current situation, or maybe at least one that's better than what they're currently doing. Now, these potential games have the following nice property. They have a potential function, phi, that with the property that if any player moves, say reducing their own cost by delta, well, then this potential decreases by delta also. Okay? And that has a couple nice properties. One is it means that better response, if there were no fluctuations, better response dynamics will reach an equilibrium. But more important for us even is it has the property that the maximum gap between the potential function and the cost bounds how bad a state could get if there were no fluctuations. So if you had a state, whether it's an equilibrium or not an equilibrium, and there were no fluctuations in it, and let's say that this potential function is always greater than the cost, but at most greater by some gap. Okay? So it's greater, but at most by some gap. Then that means that given some state, maybe it's an equilibrium, maybe it's not, people doing better response, it always causes the potential to go down. So the cost may go up, but it's not going to go up, it's not going to cross the potential, so it's bounded by most that gap. Okay? So in particular, we'll also be looking at games with a small gap between the potential and social cost. Because at least this means that without fluctuations, we could indeed walk away from a good state, one of good social welfare, even if it's not in equilibrium, and be confident that things wouldn't get worse by more than this gap. All right? Because our goal is to analyze the effect of fluctuations. So we at least want games where if we didn't have the fluctuations, things would be good. Because we're going to see what happens when we add these fluctuations to the system. Okay? And these also has a nice property that a single perturbation it won't affect the optimum solution. It can't make the dynamics do bad things. You can get rid of some equilibria, but it can't really make the dynamics do bad things. Good. So if bad things are going to happen, it's going to be through a series of perturbations and how they react, they interact with the dynamics. And then the last properties, we'll be looking at games where no individual player can influence the total cost of the system by very much. And when we have Byzantine players who were sort of imagining can do arbitrary things, our definition of social cost will be the social cost, the sum of the other's cost. Okay, if the Byzantine players want to hit themselves in the head, that's fine. They don't count in the social cost. Okay, good. So let me just give an example of a game having these properties. It's a game that I'll talk about more in a few minutes. These are set cover games. So let me describe set cover games. So set cover games work as follows. We have n players. It's these dots over here. And we have m resources, or also called sets. That's these objects over here. And each resource has a cost, C1, C2, up to Cm. All right? And each player is allowed to use some of them and not others. And that's given by this bipartite graph. The edges say which ones you're allowed to use. And here's the way the game works. Every player chooses one of their allowable resources. Okay, so maybe like that. They've each made a choice of some allowable resource. And now the players split the cost of the resource they chose with the others choosing the same one. Okay, so you think of these as like maybe wireless access points or something. Several people use the same one. You split the cost for that. Okay, so that's the game. The cost of the game, that the sum of the costs of all the players, is equivalent to just the total cost of the resources that at least one player is using. Right? Because they're splitting the cost. So it's the total cost of the system is the sum over all resources. So I'll have NE be the number of players using resource E. So all resources where at least one player is using the total cost of that resource. And it's not too hard to see if you think about it. If you haven't seen this before, that the potential, a legal potential function in this game is similar to the cost, but instead of counting each cost CE once, if it's being used by, say, 3 players, you count CE over 1 plus CE over 2 plus CE over 3. Okay? And if you think about this function, you think about what happens when a single player decides to switch from one thing to something else, this changes by exactly the amount that individual person's cost changes. Okay? You have to think about it a little bit if you haven't seen it before. One thing that's though pretty obvious is that this quantity is always larger than this quantity, but at most log n times larger because it's over 1 plus over 2 plus over 3 and so forth. So this quantity is within the cost and log n times the cost. So it's a pretty small gap. I'm going to think of log n as a small number and think of n as a big number. Okay, good. Okay, so now let me get to the model. So our model is that players will follow best response or better response dynamics, but between time steps, the cost of our resources can fluctuate between moves. So the cost of resource I at time t is somewhere between, so there's some initial, every resource I has some cost ci, but at time t could be somewhere between ci and ci times 1 plus epsilon. Okay, so it's allowed to fluctuate a bit, and that can happen between moves, and then players do best response. Okay? Alternatively, we'll have a model where the resources stay fixed, but we have a few Byzantine players who, by their movements, can change the effective cost of things to others. Play begins in a low-cost state, and now the question is, how bad can things get? Okay? And we'll define this quantity, the price of uncertainty, as could be parameterized by epsilon, as the maximum ratio of the eventual social cost to the initial cost in a game. Okay, how much bad could things get relative to where they started? Okay, so one way to look at this is we could imagine, for instance, defining a graph, a very large graph, with one node for every possible state of the system. and an edge from state U to state V if it's possible for a perturbation to make it be somebody's best response move to do something that moves you from state U to state V. Now, these are the state of the system. It's the state of everybody's play. So if you can get from this state of the system to that state of the system by some player doing best response to a perturbation, we can imagine drawing an edge in this big graph. Okay, so we create this graph among states. And now what we're really asking is, given some start state, does the set of states that are reachable in this graph contain some state of very high cost compared to where we started? So that's really the question we're asking. You know, is this sort of a safe system where you can't get, there's no kind of series of things that could get you into a bad state, or is it sort of unsafe, that some series of events could cause the system to get into a state of very high cost compared to where you started? Okay. So that's the question. All right. So the first kind of class of games I want to look at are set cover games that we just talked about. Just to get a little more feel about set cover games, they have a price of anarchy of n. So here's an example of a game where one equilibrium, a bad one, is all the players choose this set, choose this resource, n players, they split this one, they're all paying slightly less than 1, so no player has any incentive to switch to here, but of course it's a really bad equilibrium, right? If you all switch to here, that'd be much better to have only a total cost of 1. Okay, so there, the price of anarchy is n. As we said before, the potential is always bounded, though, between the cost and the cost times log n. So what it means is you get the system into a good state, and without fluctuations, a series of best response moves can get worse by at most a log n factor. And just to see a simple example where this really could happen, here the optimal configuration is all these players choose this set here. This is cost 1 plus delta. They're each playing 1 plus delta over 4, because I just do 4 of those guys. But they'll start peeling off. This guy will switch to his set here, then this guy will switch to his set here, then this guy will switch to his set here, and if this was n, it would be a total cost of log n compared to the 1. Okay, so that's an example where things really could get that bad. All right, so what can we show? So I'll show you what our results are, and I'll give a few of the, I'll select a few of the arguments to give. So for set cover games, we have good news and bad news. So the good news is that if epsilon is small enough, and the 1 over m times n, then things actually aren't too bad. Things will get worse by almost a log n factor, which is the same as they could have gotten without any fluctuations. So with this level of fluctuations, things are really not too bad. And the key point here, what makes this a good news, is this is at least, okay, it's small, but it's only polynomially small. The kind of obvious bound would be an exponentially small bound, but we can get to even polynomially small fluctuations, and still the system won't be too bad. So that's good news. On the other hand, with fairly large fluctuations, so epsilon equals 1, so if the cost can double, then things could really get worse by a factor of n. And for any constant, things can get worse by a factor of root n. Probably this should be n2, but the best argument we have is root n, the best example we know. Also bad news is that a single Byzantine player could take the state from a pure Nash equilibrium of cost order of the optimal solution to a pure Nash equilibrium of cost order n times, omega of n times the optimal solution. And that's as bad as things could get, because the price of anarchy is n. So a single Byzantine player with other players doing best response could really take from a great equilibrium to a really crappy equilibrium, the worst it could be. Okay. And I should say our upper bounds hold even for better response dynamics. The lower bounds hold even for best response dynamics. Okay, so for general fair cost sharing games, so set cover games are an example. They're an instance of fair cost sharing games, and more generally in fair cost sharing games you have a graph, you have players who each have a starting location and ending location, and they want to pick a path, and they share the cost of the edges they use with other people using the same edges. And for these kind of games, one nice thing we can say is that if we have many players of each type, so for every source destination pair, many players using that, then actually the system is fairly robust. Even for pretty large fluctuations, things will get worse by only a constant factor. Okay, although it's much harder to analyze for general numbers of players, and that's open. Also for Matroid congestion games. So Matroid congestion games are congestion games where the strategy sets are bases of a Matroid. So a simple example to think of is like the set cover games, but rather than each player choosing a single resource, each player chooses k resources. That would be one example of a Matroid congestion game. And for these, we again can inherit the nice results, the positive results for set cover games. If epsilon is small enough, then things will only get worse by a log factor. For the case where we're talking about fair cost sharing, and actually more generally, so that actually holds more generally. So in a congestion game, so I've been focusing on the case where this resource has a cost and you split the cost with everyone else who uses it. More generally, in a congestion game, a resource has a cost, and how much you pay is just some function of how many people are using it. Could be an increasing function, could be a decreasing function, just some function. And depending on what those functions are, there will be some maximum gap between potential and cost. In our case, it was log n, but depends on the functions, whether it's a big gap or small gap. But in general, as long as epsilon is small enough, things will be no worse than whatever that gap is. Okay, so that's okay. These, though, require best response. So with better response dynamics, is not enough to get these results. We have results also for other kind of games that I might talk about a little bit at the end. So let me start by giving now a couple of the arguments. So I want to give a lower bound showing how can a single Byzantine player take the system from a really good state to a really bad one. Okay, so how can we get it from a state of pure Nash equilibrium of cost order up to one of cost that's n times worse? So here's how. So I'm going to set up a system with two kinds of players. There's n players of class 1. This will be, and they work as follows. So they all have this common set where they start off there. They're all happy. They each have their own individual set. Okay, so they each have one individual one. Slightly cheaper than this, but they don't want to switch because this is expensive by yourself. Here you're sharing it with all these people. So you're only paying one there. So they're happy. We have n players of class 2. They each have their own individual set. And they can each use any of these too if they wanted to, but they don't want to. They're happy there. But there's one Byzantine player. What does a Byzantine player do? Byzantine player goes there. Now, the Byzantine player goes there, so now this guy says, oh, okay, n over 2 by myself, I can share this with this guy, so I'm going to go up here. And this guy says, oh, n over 3 by myself, I can share this with these two, so I'll go there. And this guy goes there, and this guy goes there. They all will go here. Once they've gone there, this top guy, he says, I'm n sharing with n people, or n minus delta sharing with n people. Huh, I'll go here. Now the Byzantine player goes over here and can pull all of these guys back. He goes here, here, here. Think finally he's over here. Who's left? There's a green guy here. There's this one. There's the red one down here. Who would you like to do? You'd like to share the n minus delta with the green guy or share this with the red guy? I mean, you don't really know the red guy's Byzantine, so you'd rather share the n over 2, so he moves back. So finally these are all back. This poor green guy's over here. And now the red guy, the Byzantine player, moves here. And now all of these guys will go over here. And you might argue they're indifferent between these two, so just pretend this delta is slightly bigger than that delta. And this delta is slightly bigger than that one. Okay, so the Byzantine player goes here. All these guys go here. That green one comes down. He moves them back. And he can slowly bring these green guys all the way over to here. Oh, so it's a series. Okay, good. So what it means for in this model for the situation to be bad is if there is a series of best response moves. So I'm not saying that it has to be necessarily a likely series, but that it's possible. So that there's some schedule. Right, if he moved, he would have moved back. But finally, at the end, now he doesn't want to move back at the very end. But there's just a series of yeah. So I'll get that. Good. Good. So this is an example where things could go really bad. So it starts off at some state of cost n, and gets to the state of cost n squared. All right, technically this was a state of cost n log n because of these guys. So really, really, really the starting configuration is after these have already moved here. So now the start's 2n. Okay. This actually implies the bound for the case of perturbations, fluctuations by a factor of 2, because the only thing this Byzantine player is doing is causing cost to fluctuate by up to a factor of 2. That's really the only effect he can have. There's a more complicated example if you have small fluctuations down to 1 over root n factor where you kind of simulate this Byzantine player through some series of gadgets. Now what about upper bound? So claim is that, on the other hand, if epsilon is small enough, then things won't be too bad. So let me argue why that's the case. So one thing we can do is we can think of the players in their sets as a stack of chips. And you can view the ith position in the stack as having a cost Cj over I. So if you remember the potential function, that's a portion of the potential function. And you can imagine loading the chips with value equal to the initial cost, value equal to the cost of their position. So what we're doing there is basically taking the potential function, splitting it apart, and giving little bits of value to each of these chips. Okay, so the total sum of value of the chips is just the potential of the initial state. Good. So now, think of what happens when a player moves. So when a player moves, say, from J to K, we'll just move the top chip over. Okay? Now, if there weren't any fluctuations, what would it mean? It would mean that the cost of this chip's new position, Ck over 3 in this case, would be less than or equal to the cost of its old position, Ck over 4, because that's what it means for this to be better for that player than that. Now, because there are fluctuations, it could be that he just thinks it's better because of that 1 plus epsilon. But we can't say this, nonetheless, this cost, Ck over 3, would be less than or equal to 1 plus epsilon times this one, Cj over 4. So that would happen. Okay, so now imagine that these players move, they move all around, until finally it gets into some state at the end. We care about what's the cost of the state at the end. Well, one nice thing about this game is there's at most m times n different positions that chips can be in. There's m stacks, one for every resource, and n positions on a stack, so m times n positions total. Now, any given chip could move around a huge amount. But if you look at where it ends up, and you walk backwards from where it ends up to where it started, and you remove the loops, okay? So you remove the loops. Every step is an inequality. It's this thing is less than or equal to 1 plus epsilon times that thing, and that thing is less than 1 plus epsilon times that thing. And by removing the loops, you get a series of inequalities, length at most m times n. So the cost of the final state this chip is in is at most 1 plus epsilon to the power m times n times the cost of its initial, where it initially started. So that means if you add up the cost of the guys at the end, not that you can see that last line, if you add up the cost at the end, as long as epsilon is small enough, only 1 over m times n, this amount here is just a constant. So the total cost at the end is at most a constant times the total value at the beginning, which was equal to the potential. So things don't get worse by too much. All right. Good. Now, Matroid games, in Matroid games, you can think of each player as controlling a set of chips, not just one. Like you have k resources. And the really neat thing about Matroid games is they have the property that best response is really nice. Best response in a Matroid game has the property that you can always order the move. So what does it mean to move? You have your chips in a certain place, and you move them to some other place. In a Matroid game, if that's best response, you can always order it so each individual chip is doing a better response. And because of that, we can just use the exact same argument we had before to argue that Matroid games will behave well under best response. Okay? And it actually fails for better response. You can come up with crazy situations where they start doing some weird binary counting, even with exponentially small epsilon, and get into a bad state. Good. For fair cost sharing in general graphs, if we have many players of each type, we can also show best response dynamics won't do too badly. And the high-level idea of the argument is it turns out to be very hard to analyze the cost of the current state directly with everybody using different edges. But you can track an upper bound, which is, so the system starts in a certain state, and as players move, you just track which edges get used that weren't used before, but you never drop them. So it's just all the edges that have ever been used since the start of time. This at least has so it's an upper bound for sure, and this at least has the property doesn't change too much because there's only m edges in the graph, and so edge can be used, and then which edges have ever been used over time. And as long as there are enough players of each type, because costs are being shared, if you have many players of each type, it means the average cost of any player of any given type is not too bad. It's pretty small compared to this total value C star. And that in turn implies that every change to this quantity, this upper bound C star, is small, roughly because it can never be a best response move to switch to something that's much more expensive than the average of your type. You could always go to the average. And so that plus the fact that this doesn't change too much gives you the bound. I guess I want to mention two more things. One is that our main focus has been games that have both good and bad equilibria, and kind of the question, can these small fluctuations or single Byzantine player cause you to move from a good equilibrium to a bad equilibrium? But you could also have cases where the state could even get worse than the worst equilibrium. And just one example of that is market sharing. Market sharing is kind of the inverse of the set cover game, where rather than resources, these are markets. And you go to a market and get a benefit, but you have to share that benefit with other companies that went to the same market. You have to split the market with them. That has a price of anarchy of 2, but things could get worse by a factor log n. The last thing that I want to mention in terms of results is that there's a nice class of games called these beta nice games by Auerbach, Azar, Epstein, Morocny, and Skopalik. And these have the property that the incentives to the players grow stronger as the cost gets above beta times the optimal, where beta is typically the price of anarchy. So if you have optimal, you have you have the price of anarchy sitting up here. So at that point, well, no, you can have an equilibrium, so no one's any incentive to switch. But much above there, you start getting more and more and more incentive to switch. And so those games are very nice from this perspective. And here you can show the state won't get above order beta times optimal, even with substantial perturbation or a lot of Byzantine. And just to mention some new results that are not mine, but just to mention this work of Balkan, Constantine, and Ehrlich. So they are able to show, for instance, for set cover games, they give an improved upper bound, depends only on M and not N. So if you have many players and not too many resources, that's a nice bound. Also, the lower bound that I gave had a very specific ordering of the moves. As Ava had pointed out, this is a very specific thing. But what if you have a random ordering of moves, so they still get a lower bound under the random ordering? And they also have some nice bounds for consensus games, nearly tight bounds in the effect of perturbations or on some given number of Byzantine players. Okay, so just to summarize and send some nice open problems, so we're looking at this question of when can small perturbations to the cost structure or a few bad players sort of lead natural dynamics astray. It's kind of when is it safe to turn your back, in the system, and so crazy things don't happen. We gave upper and lower bounds for a number of nice classes of games. I think in terms of nice questions, so first a very concrete question, the general cost sharing with general numbers of players, not having many players of each type, seems tricky to analyze. We put some work into it, but it seems quite tricky. Another is if you have random fluctuations, so we were thinking of these kind of arbitrary perturbations. But what if they were random? Well, eventually the worst case will happen, but maybe can you analyze this of time to failure? Could you say, well, there's a bad situation that could happen, but maybe within a polynomial number of steps, you don't have to return to look at the system for a limited amount of time. And then the last thing I think is very interesting is instance-based analysis. So in safety properties of, say, hardware or systems, people usually look at not classes, but a very particular instance. They say, here, is my particular program or piece of hardware, can this thing get into a bad state? And so you can imagine being given the description of an instance, and maybe the class has a high price of uncertainty, but this particular instance, how bad could things get? Algorithmically, can you compute, given a start state and given the description of the game, how bad things could get? I think that's a nice question. And that's it.
We can take some questions.
I have one question. It seems that you only look at cases where fluctuations can make things worse off. I wonder if it can also make things better off, and if so, if you looked at it, and by how much?
Okay, good. So the question was, we were looking at, can fluctuations make things worse off? What about can fluctuations make things better? Better. Right. So we were looking at what is the worst series of events that could happen. That's sort of kind of a safety property. But maybe fluctuations could potentially get a system out of a bad equilibrium and walking down to a good one. So I think that definitely could happen. You could have a system in a bad state and you add some fluctuations and then it goes down to good. So I think definitely one could look at that. What's that?
Whole literature on that, on perturbations and dynamics, which get into
right.
good equilibrium, for example.
Right. So like for example, things like some of the dynamics themselves, but you add noise into the dynamics, and then you get to a good state. Absolutely.
Any other questions? Okay, so don't forget to put your requests for dinner and the tour to room number 30. That's on the bottom floor. And if you feel very nice, you can do it on that piece of paper, which is on the table outside. Or you can just tell them, I think. And let's thank all the speakers once more.